Have you ever wondered how those old grandfather clocks kept ticking so accurately? The secret lies in a swinging pendulum. A simple pendulum is essentially a heavy mass suspended from a fixed point using a light, inextensible string. When pulled slightly and released, it starts swinging back and forth, and this motion is used to measure time. One complete swing from point A to B and back to A is what we call one oscillation. The time taken for this one full to and fro motion is known as the time period of the pendulum. Now let's define a few terms. The time period, denoted by capital T, is the time taken by the pendulum to complete one full oscillation. It is measured in seconds. The frequency, denoted by small f, is the number of oscillations the pendulum completes in 1 second. And here's an important relation. Capital T is equal to 1 divided by small f. In practice, instead of measuring a single oscillation, we time several and calculate the average time. So, time period capital T equals total time taken divided by the number of oscillations. Next, let's understand amplitude. Amplitude is the maximum displacement of the pendulum from its mean or rest position. If a pendulum swings from the central point O to point A or B on either side, the farthest distance it reaches from O is called the amplitude, represented by capital A. While amplitude affects how wide the pendulum swings, it does not change the time period that remains constant for small oscillations in a simple pendulum. Let's move to the experimental setup. In the lab, we vary the length of the pendulum and measure the time taken for 20 oscillations in each case. These timings are then divided by 20 to get the time period for one oscillation. This data is organized in a table and used to analyze how the pendulum's length affects its time period. What we find is, as the length increases, the time period also increases. By plotting the square of the time period on the vertical axis and the length on the horizontal axis, we get a straight line graph. This proves a key relationship: time period squared is directly proportional to length. So, time period capital T is proportional to the square root of length L. This relationship lets us determine the local gravitational field strength using just a simple pendulum. The slope of the t squared versus L graph equals 4 pi squared divided by g, where g is the acceleration due to gravity. And now, the final expression for the time period of a simple pendulum, capital T equals to pi into the square root of capital L divided by small g. This means the time period depends only on two things: the length of the pendulum and the gravitational acceleration at that place. It does not depend on the mass of the bob, its amplitude, or what material it's made of. And here's something interesting. At higher altitudes, where g is lower, pendulum clocks run slower. That's why accuracy in time measurement can even help us detect changes in Earth's gravity.